So, as I said, recursion and induction go hand in hand. And maybe more precisely what I mean by this is that you will often use induction to prove things about recursively defined objects. So let's see an example of that. So claim Fibonacci numbers grow exponentially quickly. And to be precise, so, okay, here's going to be an example where it would be hard to come up with this off the top of your head, but I guess we'll see a pattern, sort of where this comes from. So here's some setup that will not be clear at first where it's coming from, but we'll see later why this makes sense. So define alpha to be 1 plus root 5 over 2. So this is about 1.6. Doesn't really matter what it is, but it's bigger than 1 is the point. And it is the positive root of the polynomial x squared minus x minus 1 equals 0. So alpha satisfies this equation. And actually, let me point out already where this is kind of coming from. So if we rearrange this equation a little bit, what we get is that alpha squared equals alpha plus 1. And the reason that we're choosing this number to work with is that this equation should remind you somewhat of this equation. So somehow we're taking the recurrence relation and translating it into this polynomial, and a root of this polynomial will have some significance then. So let's see how that happens. So I haven't even given the precise claim yet. What is the precise claim? Then, for all n at least 3, the nth Fibonacci number is greater than alpha to the n minus 2. So this is what we mean that they grow exponentially. And that's why I was pointing out that this thing is bigger than 1. So it does actually grow when you take exponents. So let's prove this. Here's the claim. Here's the proof. So, of course, as I've been suggesting, we are going to use induction on n. So the base cases are basically just some work with a calculator. Since we used 2 previous terms to define the Fibonacci numbers, we will need 2 base cases. And I'll just write them down. The third Fibonacci number is 2, which is greater than 1.6, which is about alpha to the 1, which is 3 minus 2. So that checks out. And the fourth Fibonacci number is 3, which is bigger than alpha squared is about 2.6. Okay. And that is saying that f4 is greater than alpha to the 4 minus 2. So let's see, what can we do now? So basically now, for the induction step, let me write down what our induction hypothesis is, and then we'll say what we're going to do with it. So let n greater than 4, and suppose fk is greater than alpha to the k minus 2 for k between 0 and less than n, or between 3 and n minus 1. Yeah. So this is our induction hypothesis. So you can see that we're using strong induction because we're going to use more than one of these previous cases, corresponding to the fact that the Fibonacci numbers use more than one of the previous terms in their definition. And now how can we prove this? Well, like I was suggesting before, this defining equation of alpha is going to somehow be compatible with the defining equation of the Fibonacci numbers. And that is what is going to allow us to perform this induction. So let me write that down. Combining alpha squared equals alpha plus 1 with recurrence relation of Fibonacci numbers, we get, so let's write down this recurrence relation, Fn. We want to show that this is greater than alpha to the n minus 2. So let's just leave that there as our goal. Fn is equal to Fn minus 1 plus Fn minus 2. And these guys, we can apply the induction hypothesis to. Right, because since n is greater than 4, these two things are both in this range, from 3 to n minus 1. So they are covered by our induction hypothesis. We can apply it, and the induction hypothesis says that this is not equal, but greater than alpha to the this thing minus 2, which is n minus 3, and this thing minus 2, which is n minus 4. And now, how do we compare this to this thing? Well, we exactly use this equation. So we rewrite this as alpha to the n minus 4 times alpha plus 1, and then make this substitution. And what do we get? Alpha n minus 4 times alpha squared, which is exactly equal to alpha to the n minus 2. So in the end result, we get this inequality that we wanted. So Fn greater than alpha to the n minus 2. And there we go, right? This completes the induction step, and that completes the proof.